In section 1.8, we're going to expand on the idea of the limit and look at some ideas that we've introduced in section 1.7 in more detail. So in this section, we're going to learn how to calculate and understand one-sided limits, limits at infinity, as well as limits at vertical asymptotes. And then we're going to look at some properties of limits that we can use when we're doing limits algebraically in the next section. So first, let's start talking about the one-sided limits. That is the left hand and the right hand limit, or sometimes just said the left and right limit. The left limit is the limit if we only consider approaching the value c from the left-hand side or from the negative direction. And we use this little negative sign in the limit to denote that this is the left limit. The right limit is approaching from the positive direction or from the right-hand side, and we denote this with a little positive above the value c. So what's going on here graphically, if we think about some value c, and we have some function, the left-hand limit is just coming from the left-hand side, or from the negative direction, from values smaller than that value c. And when we find this limit, it's like we are tracing the function, just like we did in the previous section, to approach the y value that we're looking for. The right-hand limit is doing the same thing, but this time from the positive direction. We'll say positive, we'll say negative for left. So from the positive direction, and again, we're tracing the function to that point. Note that this might be the value of L, the limit, and in this case, the limit as x approaches c from the left is equal to the limit as x approaches c from the right. And both of these are equal to just the normal limit. And this is how we dealt with limits in the last section. We just talked about both sides at the same time, but we can do it one individually from each other. There's this little thing here that says, in order for the limit to exist, both the right and the left limits must be the same. So if the limit as x approaches c from the left does not equal the limit as x approaches c from the right, then the ordinary limit, the two-sided limit, does not exist, DNE. The reason why we have two different one-sided limits is because when we're approaching some value c, we can do that in two different ways, again, from the left or from the right. And it's going to be important sometimes to consider only one or the other, and we'll see some of those in this section and then later on in the course. So let's look at some examples of these one-sided limits. Here is a function, and note that this function is not continuous. There is a jump discontinuity at x equals -1, and we're going to investigate this special point x equals -1. We're going to find the left-hand limit, the right-hand limit, and then the normal limit. So first, let's look at the left-hand limit. And I shouldn't write c. We're doing from to -1 from the left. So we are looking at the x values approaching -1, and we're looking at the corresponding y values on the function and seeing what those approach. And they seem to approach the y value of 2. When we look at from the right, the limit as x approaches -1 from the right, Look at the x values getting closer and closer. Then we're going to look at the corresponding y values. And they seem to approach this hole, which is associated with the y value of 1. So then, since the left-hand limit and the right-hand limit are not the same thing, then the ordinary limit x approaches -1 of the function does not exist. So there are our 3 answers that we are looking for. Note that also we have the actual function value here at -1 is 2. And since the limit as x approaches -1 and the function value are not the same, one of the limits doesn't even exist, then we have that this is a discontinuity at that point. It's not continuous at x equals -1. All right, let's look at another example. Very similar, but this time there might be, the limits are going to be a little bit different here. So let's do it again. Let's look at the left-hand limit. That's going to be approaching -1 from the left. If we look at the corresponding y values, those are going to approach the y value of 1. The right-hand limit, coming from the positive direction, we're looking at the corresponding y values. And again, we are approaching the same value of 1. So then, since these two are the same, then that also has to be the value of the ordinary limit. They all have to be equal in that case. In this case, 1. It's the value of that hole right there. Note that this is a discontinuity because f of -1 is undefined in this case. So this is a discontinuity. All right. Next thing we're going to look at is end behaviors and horizontal asymptotes, something that we've already brought up in the last 2 sections, in the pre-calc review and in section 1.7. Now we're going to define end behavior as limits at infinity. So the right end behavior of a function, as long as we're defined on an interval going out to infinity, is given by the limit at infinity, the limit as x approaches infinity of f of x. So this is going to be our right end behavior. Left end behavior is going to be defined in a similar way, except we're going to go to -infinity, and we need to be defined on an interval going to -infinity. If either of these limits is equal to some real number L, noting that infinity and -infinity are not real numbers, then we say that the function has a horizontal asymptote y equals L. It's like it's approaching this horizontal line. All right, so that's just giving some different names to things we've already looked at. Right end behavior, left end behavior, horizontal asymptote are pre-calc ideas. Now we're just putting a limit into that idea. So let's look at an example. Determine the left and right end behaviors of this function. This is a rational function, polynomial over a polynomial. So we are looking for the limits at infinity. The limit as x approaches infinity of 3x squared minus 5x over 2x minus 1 plus 4x cubed, and the one at negative infinity as well. So note that this is a rational function, and we know some information about rational functions, especially when we talk about horizontal asymptotes. All right, we're really looking at the horizontal asymptote of rational functions. The degree on the top is equal to 2. That's the highest power we have on the top. And the degree on the bottom is 3, because that's the highest power. Even though it's not listed first, the highest power is 3. So because the degree on the bottom is bigger, then by properties of rational functions, we know that there is a horizontal asymptote at y equals 0. And that's just another way of saying that the limit as x approaches infinity here is going to be 0. Similarly, the limit as x approaches negative infinity is going to be the exact same for the exact same reasons. So as we write this limit down, we're going to get the exact same answer for the exact same reasons. So having the limits be equal to 0 is the same as saying there's a horizontal asymptote and vice versa. Note that another way that we could do this is looking at the highest power on the top and the bottom and thinking about dominating functions. We can only do this for limits at infinity. It doesn't work for limits at any other number. But for limits at infinity, we can say that this is going to be equal to the limit of just the highest power on the top and just the highest power on the bottom. And the reason we can do that is because in the grand scheme of things, the negative 5x and the 2x minus 1, these don't make a difference as x goes to infinity. And that's because 3x squared and 4x cubed dominate. Then we can say, algebraically, that this is just equal to 3 over 4x. And this, we know, is going to go to 0 because the bottom is so much bigger. If we plug in really, really big numbers in for x, that's going to be 3 over a really, really big number, which is a really, really small number. So we're going to say something like 1 over big, which is what this is going to be equal to 0. And we'll investigate that further in the next video as well. Finally, let's think about vertical asymptotes. So we're going to look at two functions here, 1 over x and 1 over x squared. And first, let's think about this algebraically. And we're going to investigate algebraic limits more in section 1.9. We're going to kind of get started right now. So algebraically, we're trying to figure out what happens to 1 over x near x equals 0. So let's try plugging in x equals 0 into the function. When we do that, we get something bad. We get like 1 over 0, which we know is undefined. But with a limit, we can say that this is going to be and we'll fill in the blank in a second here. So let's try plugging in some numbers to see what this is going to be. Now we're thinking about a numerical way of doing this. So let's try plugging in numbers closer and closer to 0. So let's make a little chart here. 2, 3 things on either side. Let's look at plugging in 1 and -1. Let's plug in 0.1 and -0.1 and not negative, 0.01 and -0.01. So that's getting closer from the left and from the right. And when we plug in those values into the function, we get 1 over 1, which is 1, 1 over -1, which is -1, 1 over 0.1, which is 10, 1 over -0.1, which is -10, 1 over 0.01, which is 100, 1 over -0.01, which is -100. And we can see that as we get closer and closer to 0, those numbers are blowing up, both positive and negative. And that's always going to happen with this kind of 1 over 0. Because when we think about 1 over 0, what we're really saying is this is going to be 1 over a small number, a number very, very close to 0, not actually 0. As a limit, we don't actually care what happens at the point. We care about what happens near the point. So this is 1 over a number really close to 0, which is a very big number. So when we have 1 over 0 and we plug in a value, that means that this is going to be either positive or negative infinity, or a does not exist. And we'll see that in a second why that's the case. So we're not quite done here. Let's think about also graphically what this means. 1 over x is one of those functions that we should just know what it looks like. It's going to look like this. Here is 1 over x. And we're going to use all this to kind of figure out the limit at 0 here. So we're going to do this 3 different ways, and we'll come back to example 5 in a little bit. All right, so first of all, we have numerically. So numerically, we're going to look at the limit as x approaches 0 from the right. And that is looking at this table just from the right-hand side. And we can see those numbers are going to get bigger and bigger and bigger, and this is going to approach infinity. The limit on the left is approaching 0 from the other direction, and we can say those numbers are also getting bigger, but with a negative in front of them. So, because these are not the same, these are not equal, then we can answer the question that the limit as x approaches 0 of 1 over x does not exist. We could have also done that graphically. So graphically, we could have looked at from the left, and we trace the function here on the graph. We're going down to negative infinity. And on the right, as we trace the graph, we are going up to positive infinity. So if we approach 0, it depends on which way we're tracing the function, and this means that this limit does not exist. All right, now let's look at the limit of 1 over x squared. This is going to be the exact same idea, except, so this is going to be the same, except when we plug in negative numbers, everything is positive. That's because we're squaring every number. This is maybe a nice way that we know that this graph is going to look like 1 over x, except that the part to the left of the y-axis is also going to be positive. So here is 1 over x squared. And in this case, whether we approach from the left or from the right, we get the same value. In this case, we trace the function, and it is going up to positive infinity. So in this case, we say the limit as x approaches 0 of 1 over x squared is positive infinity. We could do that numerically. We could also say that when we plug in 0, we get a 1 over 0, but in this case it meant both going to positive infinity. In the 1 over x case, it meant that it was actually one side going to infinity, one going to negative infinity, which meant it does not exist. You put a negative here instead, and this actually goes down to negative infinity. So the moral of the story, we'll see it later on, this 1 over 0 is a nice indication that with a limit, the answer is going to be infinity, negative infinity, or both sides going off in a different direction, and we have does not exist. And this is kind of representative of a vertical asymptote. That's what's going on here. All right. Last thing is we have a bunch of properties of limits that we can use to look at limits algebraically, which is the big point of section 1.9. So here are 7 different properties that we have. First of all, we need that all of these limits exist and are finite. And that's important because with infinity, weird things happen. And we're going to explore that in the next video as well. Or the next section, I should say. Algebra does not work the same with infinity as it does with real numbers. So none of these rules necessarily work with infinity. All right, so first thing is that if you take the limit of a constant function b, the limit is going to be b no matter what value you're approaching. You can try that or think about that with a graph. If you have some constant function here at b, no matter what value you're approaching, it's just going to be equal to that. The next one's kind of similar. If you have the function x, that is y equals x, when you approach the value of c, you're just going to get the value of c out. It has to do with that being a continuous function. All right, the bigger ones we have is things we're going to use a lot in Calc 1, and that is if you have a constant times a function, you can bring the constant out in front of the limit and then deal with the function itself. And that makes limits much easier to deal with in some cases. And this is going to be used later on when we talk about derivatives and integrals. If you take two functions and you add them or you subtract them, you can bring the limit inside of the addition and subtraction and deal with each limit separately. So you may have two functions that are separately easy to deal with, but together you have no idea what that function is, but you can deal with them separately. And the same thing goes for multiplication. If you have two functions multiplied together, you can just deal with each one separately. And that's going to be one that we use a lot. That's going to be very important. It's the exact same thing with division, with the one caveat that you can't have the denominator equal 0, otherwise some weird things happen with infinity. And lastly, if you have a continuous function f, then you can bring the limit inside of the function. So for example, if you have the limit as x approaches 1 of, let's think of a continuous function, sine of square root of x, then we can instead think about sine of the limit of square root of x. And that's because we know that sine is continuous, so we can bring the limit inside of that, and that helps us deal with a bunch of limits algebraically. In the next video, we're going to look at some more practice problems dealing with one-sided limits, limits at infinity, and vertical asymptotes, and then we'll move on to section 1.9, finishing our topic of limits.